Oh man, there's still leaves on the trees. It's only October, what, 27th? Too early for this.
Okay, so this video, boys, is going to be about actually looking at some troubleshooting on a 3-wire coil and plug system. And can you effectively troubleshoot the trigger line with just a basic digital multimeter? Some of you will certainly know, but for the uninitiated and the unfamiliar, the 3 wires typically on a coil on plug setup, guys, will typically have 2 wires that are the same on all coil assemblies, and there'll be a 3rd wire which is unique in color coding. So in the case of my Vitara here, all of them will have a black and a white, a black and an orange, but this one here will be the uniquely color coded one. As you can see, this wire is just brown, but on the there's the black and the white and the black and the orange again, but this one is actually brown and yellow. Hopefully you can see that. So it's easy enough to find the unique wire will be the trigger on a 3-wire coil on plug assembly. So we need to find out which one's the ground, which one's the power, and again, it's quite easy to tell the trigger line. The trouble comes in with the trigger line is that you're dealing with quite a small voltage that you're going to see, and what we're going to do is we're going to take a look at the scope. We'll set up the scope and actually take a look at the trigger line and understand why you're looking at such a small voltage, and we'll see if we can rationalize that and see if we can make it make sense and see if you can effectively still troubleshoot a trigger line, 5-volt trigger line in this case, boys. They may be different for your vehicle. Look at your manual. It's a 5-volt trigger line in the case of the Vitara, and see if we can make that, even though it's going to be a small voltage, in the maybe 80 millivolts range, quite a small voltage, so that'd be 0.08, quite a small voltage you're looking at on your meter. See if we can actually rationalize that number, see if it makes some sense with the use of the scope. That's the only reason the scope is involved, is to rationalize what we're actually looking at. So let's do that. So we'll turn the ignition switch on, we'll check for the power, the ground, and the trigger line, of course, will be the uniquely colored one, as I just mentioned. Okay, so I'm just going to turn the ignition on, boys, because without the main relay obviously being made, you're not going to get in the 12 volts supplied to the coil assembly. You're not obviously going to get a trigger unless the car is running either. What would be the point in triggering the coils to fire the plug if the car is not running? There wouldn't be any point in that, right? You typically need your crank or cam, or potentially a mixture of both depending on the vehicle type, in order for the engine control module to initiate the trigger to fire the plugs, of course, right? So this is the hypothetical scenario where we potentially have an issue with that. Maybe it's a wiring issue, maybe it's an ECU issue. So we want to just check that we have the presence of 12 volts ground and a sensible trigger signal, and is it possible using just a basic D.M.M, right? So let me turn the ignition switch on. You'll have to tolerate the buzz of the electronic throttle control, but what can we do? Okay, so let me start with the one line here, the black and the white tracer, and you can see we do in fact have battery voltage on that. So the next one should be our ground line, because it is again on the presence of that color coding is on all 4 coil on plug assemblies. So that's pretty low voltage. It could be potentially ground. It may not be ground. Let me just switch the ground wire over to battery positive. There we go. I didn't have a good connection there actually, but I do now, boys. So you can see by going to 12 volts, the battery negative, 12 and change negative, that is in fact the ground. So back to the battery negative. The point to that, of course, is just an open circuit may look like a ground. It may not be grounded. Just toggling over to the battery positive will confirm it is in fact ground. Mechanic Matt actually taught me that trick. Thanks, Matt. So now I'll actually start the vehicle, boys, and you'll see that we're going to have quite a low level voltage on the trigger line. Let's swap to the trigger line. Before I do so, this is the uniquely color-coded wire on the coil and plug assembly. Each coil and plug assembly has a uniquely color-coded wire because, of course, they're all individually controlled by the engine control module for the sake of timing. Okay, so just watch the meter there, guys. You can see we're actually dealing with quite a low signal. The voltage that's actually present on that line is actually quite low. You can see the meter is actually having a difficult time because this is a cheap meter. The meter is actually, because of the sample rate, if you will, of the meter, it's actually struggling to get a reasonable voltage on there. So you can see it's somewhere between 0.1. Occasionally it flickers a wee bit lower than that. Yeah, so you can see we're definitely dealing with less than 0.1 of a volt in any case. Okay, so this time I've actually got your view on the scope here, guys. You can see I've got the sweep set up for 1 second, so we're going to be able to see how many trigger pulses on the coil there actually is per second. And we'll see in the upper left hand corner there is essentially going to give us the same reading as what we saw on the voltmeter, although I suspect this is going to be quite a bit more accurate than what we saw on the voltmeter because the sampling rate is much greater than that cheap meter, so it might be a wee bit different. Let me start the vehicle, and we'll get some triggers up on screen, then we'll stop the vehicle so we don't have to talk over a running vehicle. There's the trigger pulses that are going to the coil on plug assembly as the car is actually idling. Obviously there's pretty limited number of them at a relatively low speed. You can see that the number up in the left hand corner here, guys, is actually quite a bit lower than what we actually saw on the meter, so we'll take this one as being the more accurate. You can see how narrow the pulses actually are, so the duty cycle of that trigger pulse is extremely low. What we'll do is we'll change the time base so we can actually measure the width of the pulse relative to its actual period, and we can actually figure out the duty cycle. Once we figure out the duty cycle, and we can see that it's obvious without doing any calculation that because the duty cycle is so low, the average voltage that you're going to measure on your meter is going to be extremely low, right? So that's where the scope is only being utilized with the intention of actually showing you just how tiny the segment actually is with respect to the voltage actually being present. Your multimeter will just average that, and that's why the signal is so low. It is a 0 to 5 volt pulse. As you can see, that's what actually triggers the coil, the 5 volt pulse. As the 5 volt pulse comes up, the 5 volt present, that will actually charge the primary coil, if you will. That's what actually determines the dwell, and as the trailing edge or the falling edge of the 5 volt pulse is present, as the 5 volts is removed, that's what actually triggers the igniter within the coil. So you can see it's actually only a very tiny period of time. We'll change the time base and actually see how tiny that actually is. So there you can see, guys, I've changed the time base just so we can actually see some width and actually put some cursors on there and make some sense of how narrow the pulse width actually is with respect to the period or the frequency, if you will, of the actual trigger pulse itself. So let me freeze this. Okay, so let's put a couple of cursors on here and we'll see what kind of pulse width we actually have. So that's good. Let's just go to the other one here. We'll get the total time, the period, if you will. Okay, so there's 160. Let's call it 163. We can round things off a wee bit. We're getting way too fixated with the numbers here. So let's just round it off to 163 milliseconds for total. Keep that number in mind, 163, and we'll actually look to see how wide the pulse was. And there you can see in the upper right hand corner there, guys, you can see the delta T is now down to 245. Okay, so let's keep the math basic here, boys. Math is no my strong point. What did we say? 2.45 milliseconds. We'll divide that by the total, which was 163. And that gives us, you can see there's a duty cycle there of 1.5%. That's pretty low percentage, right? So 1.5, look at the number in the upper left-hand corner there, guys, 0.05 as far as the scope is concerned. Let's take that number to do the actual calculation. So keep 0.015 in mind. I hope I'm no killing you with the math here. So 5 volts. Let's actually correct that for the duty cycle, which was 0.015. There's what it equals. Now, there is going to be a wee bit of variation in here, right? The screen is telling us 0.05, and our calculation is telling us 0.075. You have to accept that this is going to be only a relatively close number, guys. This is not going to be exact, right? As you can see, we're dealing with extremely finite numbers here. So you're going to have to accept a wee bit of tolerance. So that's close enough for my money. This is only a rationalization for why you're looking at such a small number on your multimeter. This number here is more accurate than what the cheap multimeter is going to offer. This number here is a rough calculation for what we should be looking at to rationalize the number. So I hope that makes some sense, guys, right? That number that you're going to see on your multimeter is going to be an extremely low number. Why is it an extremely low number? Let me get rid of these cursors here. Because that number is extremely low because of the width of those pulses, right? The width of that pulse over the entire duration, the period that it's actually present, is going to translate to 5 volts multiplied by a factor of that duty cycle is going to translate to that. Does that make sense? I hope so. So yes, you can in fact check your trigger with a simple multimeter, but you're going to have to accept that it's going to be a rough number that is going to be showing you 0.075 volts ish, 50 millivolts, 75 millivolts at idle. You can be reasonably sure that you have the presence of the 5-volt trigger. Start looking elsewhere. Now, of course, this gives you no clue what's going on with respect to the what's going on inside the coil and plug assembly. Is there an issue with the primary? Is there an issue with the secondary? None of this is going to actually prove anything with respect to that. Is there an issue with when the plug is actually under in-cylinder pressure? All of these are obviously factors with getting a proper spark, proper ignition in the cylinder. But with the 12 volts, the ground, and the trigger line, which you can actually check with a basic multimeter, ideally, obviously, with a scope, right? But no, everybody has one. it's a non-starter. So first things first.
So just for a laugh, so this particular scope actually has a duty cycle function, as you can see. The however, it will make a liar out of me, because you'll see the duty cycle will be extremely high. Now keep in mind, there's two ways of looking at duty cycle, right? A positive duty cycle in the case of a power switched application, or a negative duty cycle in the case of a ground switched application. So this defaults and has, as far as I know, I'm no expert on the motors, but as far as I know, only has a negative duty cycle viewpoint. So as opposed to seeing the 1.5% that we were discussing earlier, this should show us a value of 98.5%, if I'm not mistaken. Let's find out, just for the laugh.
Okay, so that's enough of that rubbish for one night, gents. Too much math for my liking. We'll call it a night. That's it. Cheers.